Hello Nadia, hello Saman, hello Asatik. Okay, so last time I think I gave you guys this work to do, and I'm sure none of you have done it. Am I right? Sir, I have done it. Okay, that's very good then. So in this one, basically you had to do was from 3 to 1, 3 to 2, sorry. 3 to 2 was like the larger minus smaller, which is minus 1.51 minus 3.4, and then EV should be 3.04, 3.024. In fact, that's what I've calculated. You can tell me if it's wrong. And then you have to do EHC upon lambda, and at the end lambda should come out as 6.63 times 10 raised to power minus 34 multiplied by 3.0 times 10 raised to power 8 divided by 3.024 times 10 raised to minus 19. It should come out as 657 nanometers, and that's basically red light. This is a photon of red light. And then for 2 to 1, you got to do minus 3.4 minus 13.6, and this should be 2.72 times 10 raised to minus 18 joules, which should be equivalent to HC1 lambda. And when you do this, lambda should come out as 122 nanometer, which is also UV light. So this photon also is of UV light. Okay, let me move it a bit up. I gave too much gap. Okay, fine, this way. So this is how this should be done. If you have any questions now, let me know, please. Sir, for the last one, I got the same answer, but the energy is not same. I got 1.63 into 10 raised to minus 18. 1.63 into 10 raised to minus 18. Maybe then my calculation might be wrong. I don't know. Okay, you can recheck it. If it's still wrong, do let me know. Okay, anyway, so now I just want you to take a screenshot of something that I'm posting. uh, Generally you would not be required, it's just something that's in the gray area of the syllabus, so I just want you to know it. Okay, just a second please. Okay, so typically this is electron transitioning, and usually when from hydrogen something jumps from 7 to 4, it's basically called bracket series. If it goes from 7 to 3, it's called Paschen. If it goes from 7 to 2, it's Balmer, and then the last one is like the highest jump is Lyman series, where it usually releases UV. So you can take a screenshot, you don't have to worry about it or anything like that. It's just that in the reference, sometimes if he gives a reference of this, you just need to know that okay, these series mean that these are electron jump groups. Otherwise with names and etc, you won't be able, they won't ask you anything related to that, so you don't have to worry about that at all. All right, so then let's go to spectra. Now spectra is basically, the definition is that spectra is called the range of frequencies that are emitted or absorbed Now, there are two kinds of basically how spectra is shown. So, first kind is the continuous spectra. Continuous spectra basically means that it is an emission spectra that occurs when a material is heated until it is white hot. So, a continuous spectrum is analogous transitions has an analogous transitions in range, frequencies with no step variation. So I'll show you this as well, so don't worry about that. Or sudden changes. Now, continuous spectra basically comes from an emission spectra, like something that is radiating. Okay, it is called, and
Ram, what is
yes,
the word after continuous? It has what?
continuous. Where did I write continuous?
It's the
Where?
second part.
A continuous spectrum. So it is called an emission spectrum because gas is excited and so light is radiated like that. Okay, I'll show you how it looks as well, don't worry about that. Okay, now we got the other one is called the line spectra. In the line spectra, is an emission spectrum of a number of discrete sharp frequencies and wavelengths of bright lines that correspond to the quantized energy gaps, which is delta E equals to hc over lambda, as you know. crap. Alright, hold on.
So could you please explain line spectra?
Yes, I'll explain everything. You just wait, okay? Just write what I'm writing right now. Because if I don't write it now, then you won't be able to get what I'm trying to show you. So, just a second. Okay. Now, first of all, I would like to tell you that first of all, we are going to look at the experiment, and this experiment is emission line spectra of hydrogen. I'm going to show you a drawing. Come up in a second, please. Hold on. Okay. So what happens is that we are giving electrical energy to the gas inside. Gas is excited, and then when the electrons de-excite, they release energy. So we throw it through a grating and then a prism. So only those frequencies basically come up, which basically refer to the photons that are released, and the photons are released because of the gaps between energy levels, and we have seen it in this one as well. Like only these three photons jump when this happens. So according to this, on the screen we see something like this. Do you guys see this? So these wavelengths that you see are basically those wavelengths of the photons that were released when this gas emitted photons. Is it clear, everybody? Now everything else on this is black because it is an emission spectra, so it is only emitting very discrete wavelengths which correspond to the quantized gaps that we know exist in any gas like that. Okay, so these are bright lines, are bright, discrete, sharp, and unique to every gas. So for like hydrogen, this is how the spectrum basically develops. For other gases it might be different. Is it clear? So you can actually take a screenshot, please. Of course you won't be able to draw this. Okay, so what you're going to do now is write about it. In case they ask you, you say that when potential difference is applied, the electrons of the gas get excited as they absorb energy and do upward quantum jumps. Now, when they de-excite, all right, and move back to the ground state, they release photons according to the jumps they have made. Now, we let these pass a grating, it is basically just to diffract them, and a prism to diffract and disperse onto a screen. So we get to see only visible light because that's what we can see actually. Spectrum, because our eyes can only detect those. Okay, now the thing is that no matter what voltage or energy is supplied, we get the same result because they will only make jumps according to their quantum gaps, nothing else. Alright, let me know if you do not understand this. Alright.
So if we use some other gas, so how will it be different? The wavelength will be different?
The wavelengths that appear, right? The colors that appear might be different at a different place. There might be multiple colors, not just four, like that. So each gas will have a unique line spectra of its own. Okay, that's how it works. Cool, right? So suppose one day you see a star, some unknown star, and then you're like, okay, let's see what gases it is made up of. So you're looking at the star, and then you see that this line spectra appears, right? This one. So you know that exactly that this basically star has hydrogen in it because the light you're getting from it basically looks like this. Do you understand what I'm saying? And if there are other gases, of course, you can compare their spectras and you will be able to know. Like that. This is how we can find the composition of so many things these days. Cool, right?
So every gas will give a unique pattern.
Every gas will, yeah, that is correct. Every gas is going to have a unique pattern. That's absolutely correct. For some reason, I messed up again, so I started the recording without the screen sharing on YouTube, so upset. Oh, nobody can see it. But chalo, it's okay. Let me fix that. Okay. Now we are going to look at this. This is some absorption spectra of hydrogen. Now, what we did was an emission spectra. Emission spectra means that the gas is emitting sort of frequencies or wavelengths that we can see on the spectra. Absorption spectra means that now through a white hot bulb, we are sending white light, which means it contains all the colors, right? And now we have a gas of low pressure, so it will only absorb the photons which are required to make higher quantum jumps for electrons. So it will absorb the corresponding photons and then let all others just go. And that is how black lines appear. Black lines appear means that these frequency or these wavelength photons have been absorbed by the electrons to make higher quantum jumps. Do you guys understand this? Okay, so we can actually write it like this. So this is basically, it is lot like continuous spectrum. Continuous spectrum just means that there is no changes. They're like all of them have the same colors, like there are no lines. This is continuous spectrum. However, it has few lines missing. Okay, so because I drew it with hand, so you might see step variation, and I basically put dark thick lines. They're not thick at all, they're very thin lines. If there is only one frequency, few of them, so just ignore that. Now I'll show you from Google as well how they look. So a clear glass chamber containing low pressure gas is used. A white hot source of light is given to the gas. The electrons in the gas absorb only the photons corresponding to the quantum gaps, which are unique to quantized levels within the gas. That's what you guys need to understand. Okay, so those photons of specific wavelengths are absorbed, hence black lines appear like that. All right, so I'm going to show you the last thing for this chapter and then we're done. I can't believe we finished in 4 lectures. I can't believe this. That's cool.
So can you show the diagram for a minute?
Yes, please just take a screenshot. It's very hard to make. It's fine.
Done.
So I just make these diagrams. I've made them once when I was developing my work because these diagrams basically will help you in paper 5. more or less, right? So you should always look forward to them, because that's why I label everything just like we would do in paper 5. So you should always remember that. Okay. Now I'm going to show you a summary of what we've done right now, and then I'm going to show you uh, the other things. I hope it will sync soon, because the image is very, 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 very big. Okay, go on, sync, sync, sync. Okay, I messed up actually. Sorry. I just destroyed your notes because of the syncing issue, you know. This has come on this. Whoa, no. Damn. What will I do now? What can I do now? Okay, wait. Let me undo. I can't even undo this. Chalo, koi baat nahi. We'll copy this. What is this? Okay. And the rest of it, I just need to remove. I have to remove everything now, basically. Okay, go on. Go on. Okay, I'm sorry about that. Oh my god. All my hard work has gone. Okay, I think it's fairly clear now. Wait a second, please. Let me fix it too. It's no good. That's this way. Well, I gotta share these notes to you, and I'm not too happy about it. Please don't do that. Okay, fine. That's there. Okay, so the summary that I wanted to give you was that a continuous spectrum means that if you like make something red, like white hot, and then you basically it will keep on releasing photons, and then you're gonna get something this no step variation, everything is like mixed up. This is a continuous spectrum. Now if you increase, like if you heat a gas and then let it, when the electrons de-excite, they're gonna basically only show those photons which are released by them according to their quantum gaps. And then if you pass like photons through a cold gas, it is going to take the corresponding photons, absorb it, and then only let the other ones go. So you will have absorption spectrum where black lines will appear, right? So this is what the crux of all this is. Is it clear? Any questions? Okay. So it's so sad you guys never appreciate my drawings. That's so sad, you know. Okay, let me see who's in, who's not. Okay, yeah. Now, who's Rafe Arif? Who's Rafe Arif? Rafe, do I know you?
Me?
Oh, Rafe. Oh, it's you. Okay, I thought somebody else. Okay, wait. So, continuous spectrum.
It is someone else.
There's also some other Rafe, right?
Yeah.
Rafe, who are you? Rogue, rogue member of this class. Okay, I don't know. All right, so continuous spectrum basically. Okay, this is a good picture actually. This is what I want to see. Okay, go, go, go. Where did it go? Oh no, wait. This is what I want to see. Okay, so if you look at this, you might see that continuous spectrum in this one is like. Sorry, this is your first class. First class, Rafi. Okay, well, all right, that's good. All right, so continuous spectrum means that basically it's like all the colors are like mixed like this, right? Emission spectrum would only emit those lines which are the ones of corresponding wavelengths. So those photons come up, right? And absorption ones, the same lines. If you look at both the spectrums, like you see that the black lines appear exactly where the colored lines were before. Because either you're emitting or you're absorbing, the quantized gaps are going to be the same. Do you guys understand my point? Just like that, okay? So I hope you guys have an idea what I'm talking about. And usually, I don't know how I will ever go back from this state. Okay, please go back. For some reason, huh? I probably zoomed it so much. Okay, I'm back. Usually, na, if I say spectrum of, let's say line spectrum of different gases, right? Usually your questions will be related to hydrogen. So here is one of the pictures. So you might see that this is how sodium looks like, and they have different line spectrums, like nitrogen has different, and hydrogen different, and oxygen. Do you see? Gatika, is it clear now?
Yes, sir.
Yeah, like that. So if you're looking at something like some planet, something really far away, so you can actually know the composition of that by using this technique, which is like now widely popular. So thanks to Einstein and of course Mr. Planck. Okay, now let's go
So
to
what's the difference between absorption and emission? I don't get it.
Gatika. In emission, it's only emitting those photons, rest of it's black. Okay, those photons which are according to quantum gaps. What I mean by this is, like if you look at the picture that I showed you, you see in the absorption one, the black lines are those lines which photons are absorbed by that gas. Do you understand? Because you're sending, like from a source, you're sending all the type of light towards it, and it's only taking those photons which it requires. Do you understand? So it's absorbing those photons. Got my point? And if you
Okay.
heat up the gas, and now when it de-excites, so it's only producing, like if you look at here in the first line, which is close to 400 nanometer, the black and the purple basically upside down, they're the same. Like everything else is back, only those photons are being emitted which are emitted by the electrons when they're moving down from the energy level. Do you understand?
Yes, sir.
Yes, so you do remember that. Okay, that's cool. Now, the thing is that, of course, my these are like the questions are quite simple. What you're gonna do is you're gonna go to quantum physics like that. From this, I'm gonna share you this time. Okay, and then in this one, there are a couple of things which we will do in say medical physics separately, but for now you just need to remember this. That's all you need to do. Now, questions like these explain why, for the photoelectric effect, the existence of threshold frequency in a short emission time provides evidence of particulate nature of electromagnetic radiation, as opposed to a wave theory. Now, this is 4 marks, right? So basically, when you go to the notes, you will find that we have done it exactly somewhere, I think here. So you will write this for the wave theory, and you will write the observations from here for that. So basically this would be the same. Now you just need to remember that. And then it says state explain two relations with Planck constant, and the constant is the constant of proportionality. Explain two relationships in which first of all, Planck constant, if you go again to the notes, the first time we used Planck constant was when we did the math behind it, right? So let me just show you that as well, so you guys can, whenever you're doing these questions, please open the notes. It's very important. The first formula that used this was E is equal to hf. This is what we did, electron photon energy, and the math behind was that the relationship is it's basically directly proportional like that, and this is the gradient here. And then the next thing we did was for the de Broglie wavelength, where it was lambda was equal to this, so you guys need to write that here. Anyway, and then explain how a line emission spectrum leads to understanding of the existence of discrete electron energy levels. This is basically, I've written the 3-4 points. You got to write it for the emission line spectrum as well. And then these are the wavelengths basically shown, and they say, okay, you need to find photon energy. So E is equal to hc upon lambda. You can find the photon energy here, and so on and so forth. So I'm sending this PDF to you people. All you don't need to do is, you don't have to do anything related to X-ray, and you don't have to do anything that is related to, you got to do this, related to CT scan. Let me see if there is CT scan in this. And if anything you do, you will find that in notes. So no need to do this X-ray imaging. This is not required. Should I send you this 100-page PDF so that you can do it for live? What do you guys say?
100 pages.
It's only 100 pages, Kartika. Only.
So only 100.
Yeah, because actually you have to do it sometime, leaving all this.